Multivariable Calculus, Lesson 14.7, Day 2. We're going to apply our lesson on finding extreme values, local max, local min values, to optimization problems. So you can look at our learning target. I can solve multivariable optimization problems. And here's a classic question. It should seem very familiar. From what you did in single variable calculus, you would have found the distance from a point to a curve. Here we're going to find the shortest distance from a point to, in this case, not a curve or a solid in 3D, but just a plane. You could still think of that as a 3D surface. What you can immediately remember is that whenever we're discussing finding distance, of course, we're going to use the distance formula. And, even as we go into 3D, it looks very reminiscent of what you would have been doing for years. It's just now we throw in a z component. And it looks just like so. So, this first point that we have right here, 1, 0, negative 2, we could call that our x1, y1, z1. And then we're going to have an arbitrary point on this surface, on this plane, x, y, z, but we'll consider that to be our x2, y2, z2. So there certainly is some point on that plane that is closest to the point 1, 0, negative 2. So let's go ahead and start writing this out. Our x2, I'm just going to write as an x. It's some arbitrary x value on the plane, minus a 1, and we will square that. We'll have a y minus, well, our y1 is 0, and then we'll have our z minus, well, this will be a negative 2, and that'll be a negative 2 squared. So you can see right here we do in fact have a function d on this left hand side. It looks like it's represented out of 3 variables right now. However, if we go back to the equation of the plane, and by the way, the y minus 0, we don't have to keep writing that. We can just write y squared. And then this becomes z plus 2 squared. Take a look at this thing right here. We can go ahead and solve for z. We can say z is 4 minus x minus 2y. That's what the z coordinate is, and we can substitute it in right here. And I hope the reason makes perfect sense when we do that. When we go ahead and replace z with this 4 minus x minus 2y, what you've essentially done is you've now written this distance formula in terms of a function of x and y. By the way, that's really what we were looking at yesterday, where we had a function of x and y, and we can clean this up very quickly. We can say, hey, a 4 and a 2 add up to a 6, and we'd have a 6 minus x minus 2y quantity squared. Well, it's been a while since you've been involved in optimization problems, I'm sure. You might remember that in single variable calculus, when we were optimizing distance to curve problems, we said that whenever d, that distance, is greatest or smallest, a wonderful fact is d squared would simultaneously be biggest or smallest. So a wonderful trick that we can do here, a wonderful shortcut that we can have, is we can say, you know what, let's just consider the function, say a capital D here, for d squared, and we can say, hey, if we can find out when this function d squared, or capital D, is biggest or smallest, in this case we want it to be smallest, then little d would also be at the same extreme. So minimize capital D, you're also minimizing little d. So why do we do this? Well, now our derivatives, thank goodness, we don't have to go through the pain and the frustration of trying to take derivatives with the square root. Well, tell you what, I'm going to take a derivative with respect to x, and hopefully that's not going to be too bad. We'll have a 2 times x minus 1. And then, of course, this y squared goes away, but as we take our derivative in here, of course, the 2 is going to come down. But inside the derivative of negative x is going to be a negative 1, so a negative 1 is going to come out. So that's going to be a minus 2. And then we have a 6 minus x minus 2y, now just raised to the first power. So the 2 comes down from the derivative of the outside. Derivative of the inside, of course, is a negative 2. We could clean this up, and it's actually a smart thing to do. This is 2x minus 2. This is a minus 12 plus a 2x plus a 4y. And it only takes you a moment to see that the derivative of this function with respect to x is a 4x plus 4y minus, well, negative 2 minus 12 is a minus 14. And by the way, we could set that equal to 0 to try to help us find critical numbers, and we'll get to that in just a moment. But you know what? Likewise, we can say, look, we could find the derivative with respect to y. And when we do that, well, we'll have a 2y, and now we're going to take our derivative right here. We're going to bring down a 2, and we'll have a 6 minus x minus 2y. But look at the inside. The derivative of the inside would be a negative 2. So as we take this derivative with respect to y, we're going to have the 2 out in front and then multiply by another 2. Hope that makes sense to everybody. We'd have this. And if we just clean this up quickly, we'd have a minus 24 plus a 4x, and negative 4 times negative 2 is a plus 8. That's a plus 8y. So what are we left with? Well, I hope you can agree it's 4x plus 10y minus 24. And that's going to get set equal to 0 also. Now, when we're setting these derivatives equal to 0, I hope it's pretty clear. The reason why is we would like to find these critical points. So tell you what, if we just go ahead and recopy this equation off to the side here, we have a 4x plus 4y, and we add a 14 over. I've switched left and right sides, and I moved the negative 14 to a positive 14 on the other side. I tell you what, we want to get rid with elimination. If I were to multiply this other equation right here by a negative 1, we'd have a negative 4x to cancel out the x minus a 10y, and we'd have a positive 24, but then when we'd bring it over, it would be a minus 24. So that when we add this together, we'd have a negative 6y is equal to negative 10. And if we divide by negative 6, I think it only takes a moment to see y is equal to 5/3. Now with y equaling 5/3, we could come back here and let's divide out a 2, even to simplify this just a tad here. We'd have 2x plus 2y equals 7. If we were to plug in our 5/3 here, it's only going to take us a moment to clean this up. Let's see, this is 2x plus 10/3 equals 21/3, and that's going to be 11/3. And of course, as we divide by 2, we will get 11/6. What did we just find? Guys, you know what? You found your critical point. You found your critical point. So I'm going to bring this back over here and say, hey, we've got our critical point. Our x was 11/6. Our y was 5/3. And, we're almost ready to finish this up. You know what else we need? We need to find a dxx. We need that second derivative right here. The derivative of the 4x plus 4y minus 14 with respect to x, that's going to be a 4, isn't it? And we need a dyy. Well, if we went to our dy right, right here, and we could even say dy was 4x plus 10y minus 24. Take a derivative with respect to y, and you're going to see you get 10. So we'd get this right here. And then we should also find a dxy. Well, a dxy, well, if we go back up to dx, and now we take our derivative with respect to y, you'd just be left with a 4. So we're going to finish with that little table that we had. We're going to have our point, and then we have our discriminant. This is what we did last lesson. dxx times a dyy minus, we'd have a dxy squared. We're going to have to compare that sign with the sign of dxx, and then we're going to have our conclusion. So the point in question is 11 over 6, 5 over 3. And the funny thing is, these second derivatives right here, you don't have to plug anything in. My goodness, it's 4 times 10 minus, this is 4 squared, so that's 40 minus 16. And guys, that's positive, isn't it? It's definitely positive. And then dxx, well, we saw that already. That's a 4, and that's positive. And you might remember when a second derivative was positive in single variable calc, we thought about being concave up. So this means we've got a local min. We've got a local min here. And actually we're going to be able to take it further and know that this is actually going to be our absolute min in the context of this problem. So we're going to be able to, in such a situation, go a step further and say it's going to be an absolute min. And we can say, well, what exactly is it? We've got this absolute min of, well, we'd like to find what's going on. And actually, I think they want us to name the point. So we're going to say it's an absolute min at, we'll name the other situation in just a moment, what the shortest distance really is. Here's your x, here's your y. Your z was on the plane. You might remember it was this thing, right? It was 4 minus x minus 2y. That's what we had right up here. Okay? So if we were to plug in 11 over 6 and 2 times 5/3, as we're working this thing out, let's see here. This is going to be 4 minus 11. Well, we can even get a denominator of a 6 right here. This is 24 over 6 minus 11 over 6. This is 10/3, which becomes 20 over 6. And wow, if we're not mistaken right here, 24 minus 20, that's a positive 4. And positive 4 and negative 11 make negative 7. So that's negative 7 over 6. So it's an absolute min, an absolute minimum distance at that point. That's the point on the plane. The shortest distance would actually be found right here. Remember, we're not going to be plugging into capital D. We'd have to do that. Now, we're running out of time on the video, and I don't have time to crunch all of that out on the calculator, but you may confirm it. They didn't ask for that. What they asked for was find, I am so sorry. They want the shortest distance. Sometimes they want one or the other. They'll ask for both. It's going to be, I worked it out, 2.041. If you plug that point into that distance formula, but sometimes they do want you to find the point on the surface that would correspond to the shortest distance. You have to read very carefully what they're asking for. but we found both of them. Good luck.